Now we'll go on to the next session titled Apache Kudu, Updatable Analytical Storage for Modern Data Platform, led by Mr. Sho Shimauchi, Sales Engineer at Cloudera. Now please welcome Mr. Shimauchi.
Thank you for coming. Today, I'm talking a bit about Apache Kudu, one of the Apache Hadoop ecosystem project. And probably it's new for most of people in this room. But it's something you should start looking at. And I hope to tell a bit about it today. But before now, I talked about Kudu. Let me introduce myself and my company first. My name is Sho Shimauchi. I'm a sales engineer and technical evangelist in Cloudera. I joined Cloudera in 2011 as its first employee in Cloudera APJ. So if you have any questions, please feel free to email me, or if you have a Twitter account, just also you mentioned it in Twitter. So I think some people who knows Cloudera as a Hadoop distributed company, but now Cloudera is not only for Hadoop distribution, but also enterprise machine learning and analytics platform. Cloudera was founded in 2008 in the Bay Area in US. But so when I joined Cloudera 6 years ago, we have only 70 people as an employee. But now more than 1,600 people work at Cloudera. One of the most important customers is Rakuten Card. I think some guys from Rakuten Card from here today. But Rakuten Card selected Cloudera for the replacement of mainframe system with Apache Spark, one of the most popular open source distributed processing frameworks. Kobayashi-san from Rakuten Card will give us a keynote at Cloudera Tokyo, which we will held in next month. So, if also you're interested in details of a project, so please come to this event. Before, I talked about Kudu in technical details. So, let me try to show some kind of short introduction about Kudu. So first, so please raise your hand. So who have heard the name of Kudu in this room? 1, 2, 3, 4, 5. So OK, thank you. Yeah, it looks not so many people knows about Kudu, but yeah, that's why I introduced Kudu in this session today. So this is a stack diagram just showing the overall capability of the Cloudera platform. And the highlighted part in the right bottom now is Kudu. Kudu is a kind of storage engine. So it's not a processing framework. It's not a streaming engine and so on. And also, it doesn't SQL on its own. It just stores data. The difference from where it was before from other storage engines is what we will talk about it today. But before I get into a lot of details, so let me go back to step back to a couple of years ago. So sometimes our customers and users, or maybe you guys, think so Hadoop ecosystems has too many components. And so they're always adding new ones, and so we cannot handle the components, and we cannot keep track of which one to use. So the decision we add new components is something we don't take too lightly. But so why did we decide to add a new one? In 2012, the founder of Apache Kudu, Todd Lipkin, found that our customers and users have actual problems of using existing two-storage system named HTFS and HBase. So this is a graph shows the difference between the two storage systems. Basically, you can say that HDFS is kind of some kind of traditional Hadoop storage system, or so you can put both stores like Amazon S3 in that quadrant as well. It's very good at an append-only kind of barcode use cases. So when so you dump a bunch of data in, and then you want to scan the old data back and do some aggregate analysis or some kind of run from SQL queries and run some machine learning or model building and any kind of data movement type operations. But if you look at the further edges of the two axes, it's not so good at real-time workloads like random access or storing data and so on. So HDFS is just only kind of block-oriented or maybe blob-oriented storage. HBase, on the other hand, also it's very good at random access or streaming processing. So you can do single row updates or insert and SOS runs a couple of milliseconds at a time. It gives you this NoSQL style API. But if you try to run some kind of SQL query or a Spark job and top up HBase, you usually be disappointed at the performance. So we've seen over the past years before Kudu came along, people build complex hybrid architectures, sometimes called Lambda architectures, that kind of tries to bridge this gap between the two. So where you're putting some data in HDFS and then some data in HBase and defining some kind of union or data migration. And so yeah, this kind of architecture becomes very complicated very fast. So that's why we developed Kudu. So the goal of Kudu is to fill that gap. So, but we're not trying to develop a better HDFS or better HBase and so on. So there's still many engineers working on HDFS in our company, and still we have an HBase team now working at HBase. These storage engines are great for their particular use cases, but Kudu is trying to be this kind of middle ground that's pretty good for everything. And that makes your application architecture much simpler because we can do both analytic data operations like HDFS can, and also we can do low latency single row operations more like HBase. So the elevator pitch is kind of scalable, fast, and tabular storage. So scalable meaning we've tested about 100 node clusters. One of Kudu clusters, Kudu users, Comcast, gave a talk recently about the cluster they've got around 400 nodes at this point. And the design is meant to scale the same kind of sizes as other Hadoop ecosystem components. We haven't tested the 1,000+ node yet, but the design should scale. In terms of speed, of course, we expect the speed to be pretty much linear with the number of nodes, the resources in the cluster. So each node should kind of give what you expect, multiple gigabytes per second with throughput given today's storage, and millions of random operations per second. And then you can scale that by the number of nodes in the cluster. And the data model is tabular. If you can imagine a relational table with a schema and types and columns and rows and primary keys, and we store those into Kudu. So we're not a file system. We're not trying to compete with file systems. So we just store tables. So you can have any number of rows in the table, and hundreds of billions of rows is completely reasonable, but it is a strict schema table. Also, Kudu has a pretty large community, and it's growing. Kudu is an open source project in Apache Software Foundation. There are a lot of contributors and committees from a lot of companies. Let's talk a little bit about use cases. Sometimes you want to have data ingest time series data arriving from the sensors all over the place, or you may want to do some kind of machine data analytics, which requires to perform the large-scale scans over terabytes or even petabytes of data. At the same time, you may want to do some kind of online reporting integrated with existing tools like Apache Impala, analytical SQL engine on big data. These kind of use cases are the user-oriented motivations why we developed Kudu. So let's talk a little bit more about technical motivations. There are new trends in the hardware market. So first of all, solid-state storage like SSD is getting cheaper and faster every year. Also, we are observing the arrival of new storage technologies such as 3D XPoint, which is now called Optane. Kudu was designed to take advantage of these technologies. Secondly, memory is getting cheaper and bigger. So 5 or 6 years ago, most of our customers has this, servers which has 64 gigabytes or maybe 128 gigabytes of RAM in their worker nodes, but now 256 gigabytes of RAM servers is so common. And we designed Kudu to run smoothly on this kind of huge RAM. We wrote Kudu in C++ to avoid GC issues because 256 gigabytes is too big to run some kind of GC operations. This was one of the main motivations to write in C++ beyond some performance advantages. And finally, we need something that is efficient on modern CPUs. CPUs are getting more cores and the vectorization bandwidth, but not necessarily gigahertz. Kudu was designed to take advantage of SIMD instructions and to use concurrent data structures. So let's move on to the technical details of Kudu. First, I'll talk about replications and fault tolerance. Kudu has a couple of concepts you need to be familiar with: tables, tablets, and tablet servers. If anybody here is HBase users, it's same to regions and region servers instead of tablets and tablet servers. Or if you are familiar with Cassandra, tablet is same to vnode. So we take each table and split it up into little chunks we call tablets. This is horizontal partitioning, meaning that any given row you can figure out which tablet it goes to. One difference from other systems is that we support different ways of partitioning. We call it flexible partitioning. So for example, if we want to partition by a hash on the timestamp, so you need to go this in the other systems by prepending that hash into your primary key, doing a lot of Java coding and byte array manipulation. We call it sorting. This is a kind of a more advanced HBase thing. Kudu does this for you for free. You can just specify when you create a table distributed by a hash or timestamp and hundredweights, and then Kudu does it for you. So you don't worry about anything. So it will optimize queries based on this. Basically, it simplifies your life. Every table also has a primary key. Again, familiar for other key-value store, except that because we have schema, our primary keys actually encode the types and the idea of composite keys. So maybe for a metrics database, you might have host metrics and timestamp, or for network monitoring, you might have source IP, destination IP, and timestamp, something like that. So we were very flexible. You can arrange partition, or you can range partition, or you can hash partition, or you can combine the two in different ways. Of course, it can get complicated, but the simplest thing is probably just hash partition by timestamp. You're good to go. So each tablet, each chunk of the table also has a bit to be replicated, and Kudu does its own storage. We don't use HDFS or anything else underneath. We handle replication at database level, so each tablet has 3 replicas or 5 replicas, and we use an algorithm called raft consensus, which is very similar to Paxos, if you have heard about that. Or no, it's also very similar to how Zookeeper is implemented. It's a general family of algorithms called consensus algorithms. And if one of these replicas crashes, the tablet server went down or starts swapping and is basically unavailable, we elect what's called a raft leader within about 5 seconds, and there is no long mean time to recovery. There is no log splitting, everything just fails over. Good to go should be a zero impact to client as long as the client timeout is no longer than the 5 seconds for failover. We also have a master process which is similar to other systems. Of course, master process is replicated as well. Master server mostly does simple operations. It keeps track of which tablets exist, which tables exist, and what the schemas are. It also does a little bit of policy management for the clusters of stuff like the load balancing. If a server is down, and we need to create new replicas, we replace the ones we lost, the master makes the policy decisions. But it's important to note, no data ever flows through the master. It's metadata only. And because of that, it's a very small amount of data, and because so now we have so much RAM today, we cache all of it in RAM. So the master keeps all the metadata cache in RAM, processes on disk, of course, for durability, but cache in RAM. And we see 99th percentile request to the master be under 100 microseconds. So it's very, very fast. It's just doing quick lookups. Let's quickly illustrate this point. This is a diagram. We have on the top left a client. This is a client library written in Java or Python or C++, and it wants to read or write row whose primary key is tlipcon. So tlipcon is the name of the founder of Kudu. So the table, maybe an employee's table or something. So it goes to the master and says, hey, where is this row? And the master responds saying it's part of tablet 2. Well, it's on these particular servers. It also piggybacks on other information about nearby other partitions or other tables. The client caches this information. It's okay if this client's cache becomes stale. It can automatically invalidate and refresh. And then the client will send these updates directly to the leader replica of that tablet. In this diagram, the update operations go into tablet server Z, which has a leader replica of tablet 2. Again, the leader replica is elected on the fly. It's not a static property. They let you know when the tablet comes up. They talk to each other vote and ready to go. So when the client actually sends the updates to the tablet leader, it will send a write RPC. This is all the implementation of the client. So if you're a user, you don't care about this at all. It's all under the hood. The tablet will then write it to local write headrock for durability and also replicate the write to the two follower replicas. These replicas write to their write-ahead logs, and as soon as they've done that, they respond that says success. And as soon as the leader has seen the majority of the write-ahead log write succeeded, so that's source of the guarantee that this write will never be forgotten. So there's no case in which it could be rolled back or forgotten or corrupted. This is not eventually consistency, but this is a strict consistency. So the details might get into a lot of academic stuff, so I won't go into them now. But basically, the key things here is strict consistency, serializability of operations. So when the leader has achieved this majority, it can respond to the client. So if the client gets success, your right was acknowledged that guarantee we will not lose that right. If we lose that right, our support team and the engineering team will stay up all night worrying about it and treating it like a highest priority bug. So this is our primary guarantee. So diving a little bit into the columnar storage, which is actual on-disk storage of Kudu. So I don't know if people here are familiar with the columnar storage or not, so I will show a quick primer. We have an example table here, which is the Twitter Fire Force. The Fire Force term, if you don't know, so it's basically a table of all the tweets that ever happened. So it's a kind of a streaming insert workload. Probably it's very wide. So in this example, I just show the 4 columns here, but luckily it's dozens of columns actually. And we have a couple of example tweets, and in the traditional raw store database, we actually would see this laid out on disk in essentially the same order you would read it, where first we have all the data for the first row, we have all the data for the second row, and so on. So that's kind of the natural way you might lay out the data, like the TSV file or CSV file. Because this is raw storage, if you want to do some huge scan, you have to read all the data, even if you read 1 or 2 columns in that query. Also, you cannot use encoding trick for the data. I will talk about encoding later. On the other hand, columnar storage is different. We actually have a separate file, but not technically a file on disk, but you can think of it separate files, separate block for each column. So we have all the tweet IDs into one file, all the username into one file, and all the creation timestamp or all the text. So this initially seems kind of crazy because when we read one row, we're going to have to do all this. All this work to look at 4 different files and reconstruct them back together. Maybe we are doing for disk 6. And you're right. Random access on column stores has traditionally been considered crazy. But now we have all this RAM and all these very fast read devices, and this trade-off completely flipped, because doing for random accesses on the persistent device is like basically a sub-microsecond. This is not something you have to worry about. For random access on the disk drive, it will take maybe 40 or 50 milliseconds. And some order of magnitude hardware changes is why we can now promise random access with a column store. So let's move on why we choose columnar store now. So the first thing to consider is column sizes. Here we have 4 different columns. So like the text columns, so the actual text in the tweet, is probably 100 to 200 times bigger than these other data columns like timestamp or tweet IDs. And imagine you're an analyst and you just want to say how many tweets does this particular user do. You're gathering some statistics and you want a fast interactive response. To execute this query, we're reading the username column. So we just read that one column, so read around 2 gigabytes of data. So we don't need to parse or we don't need to do any I/O for other columns. So we're avoiding reading 200 gigabytes to serve this query, reading 100 times less data, and consequently, you can expect the query to run 100 times faster. So for analytic workload, this is where we get very good performance. And this is also an area where vendors like to cheat and say, my database is 10 times faster, or my database is 100 times faster, or 1,000 times faster. Yeah, so you can pick now how many times faster you want Columnar database to be by just adding more columns. Of course, I could add 10,000 columns, just read one, and I could just say my database would be 10,000 times faster. So please always be skeptical when evaluating comparisons of Columnar and raw stores. It's really worker dependent. But many workloads have this pattern where most analysis accesses minority of columns. The other big trick we can do when we store the byte columns is enhanced compression. So take the creation timestamp columns, and if you look at these numbers, they all start with the same 6 digits. It's a kind of waste to continue to use all of these bits every time. So instead, what we can do is store the difference between these 2 columns. This is called differential compression. And the difference tends to be a lot of smaller numbers. They only needed 11 bits each, whereas the original ones we were needing 64 bits each. A lot of actual workloads, this can compress even down to 1 or 2 bits per entry. So you're getting many rows packed in the single byte, which is very much better than you can do in a row-based storage system. We've got a few bits per row instead of few bytes per row, and this works great for timestamps and time series values that change infrequently, but are measured frequently. Low coordinated strings can also use the things called dictionary compression. So people tend to store enumerations or other kind of like city name or something like that, or state name. It's not as many states. You don't need 8 bytes per state, but there is some pretty long state name. Kudu will figure this out and code your states in 6 bits where whatever the minimum number of bits are required. So this saves you a lot of spaces, which is good because the fancy new hardware isn't that cheap. It's getting cheaper, but it's not free. And it also improves your performance because you don't need to read much for the same query. So let's move on to the next topic, write and read passive. It will show how Kudu technology is different from the other storage engine. I'll compare Kudu with LSM, log structures merge tree, which is a technology-backed Cassandra, HBase, and other storage engines. In LSM, inserts and updates all go to in a memory map. Update doesn't need to check the existing data, but read operation needs to merge all data together. Kudu shares some trait with these storage engines like memo stores, compaction, etc. The write path is more complex and slower than LSM, but Kudu can gain faster reads with this implementation. Let's see how LSM works first. I'll show this example as H-based architecture, but other storage engines like Cassandra have almost same design. On the row insert into an LSM, it goes into memory store called memstore in HBase. HBase periodically flushes memstore into disk called H-file. The more inserts comes in, the more H-files we have. Update operations also go into memstore, and it doesn't need to look at H-files which exist to know where it need to go. This is the key difference between the traditional LSM and Kudu. However, this comes at cost, more complexity on the read path. So on the read path, now we need to merge memstore and all the H-files that cover a certain range. Moreover, in HBase specifically, merge is based on string row keys. Now, this is CPU-intensive operations, and you always have to read the row keys. The more H-files are need to merge, the slower read operations become. This is the reason why traditional LSM storage engine is not good for large-scale analytics. Let's see how this works on Kudu. Like traditional LSM, insert goes into Kudu memory store named mem_row_set. And later, it gets flushed into disk row set. The flush file in HBase is a single file, but since disk row set is columnar file format, Kudu flushes multiple files for each column. There are two types in disk row set. The latest version of a row in the mem_row_set is written to the base date file, so that is one of the data types in disk row set. I will talk about the other type of disk row set later. More insert comes in, more disk row set we have. As you see, insert path is almost same to HBase. But update path is pretty different and complex. Update operations goes into delta memstore instead of mem_row_set. It's same to mem_row_set. Delta memstore is a memory store. Each disk row set has its own delta memstore, which accumulates all of the updates for the disk row set. This means that each key only exists in one disk row set. If we want to update a certain value for a certain column, we first need to check the disk row set by querying Bloom filter. If Bloom says no, this means the row doesn't exist in the disk row set. And then we need to check another disk row set. If Bloom says maybe, we usually go into the disk row set and look index. When we find the query we are looking for, then we add the value to the data memory store. Again, the difference between Kudu and traditional LSM storage engine is that Kudu has to do much more things for update operations, like as I talked in this page. However, the big can comes of read path. I'll talk it later. So what happens when the delta memory store runs out of memory space? Like mem_row_set flushes delta memory store into a redo delta file. This is a file which needs to be applied to base data on the left to have a most recent version of a single row. Of course, over time, this needs to be accumulated. So when we have many redo delta files, this causes a problem because we need to apply delta to each one of the row in base data to have the latest version of the row to provide a scan to give back to users. So we need to optimize these operations. These operations is called compaction. There are two types of compaction, minor delta compaction and the major delta compaction. Minor delta compaction is pretty simple. It merges small redo delta file into big one. Base data is not touched in this process. On the other hand, major delta of compaction is a little bit complex. We do this by merging updates for high-frequency update comms. For example, the pay comm, which is updated more frequently than name or role comms. Kudu merges updates only for pay comms, and it leaves updates for the other comms, which updates are more rare. And put previous version of the row into undos. This is the second type of disk row set. Undo records contains previous versions of the row that allow Kudu to perform historical queries, so Kudu can do consistent scans called time travel read. I'll talk this in the read path section later. When Kudu flashes mem row set into disk row set, data is sorted in dictionary order. On sorted data, if you see certain end row of the data, you can easily find a certain row exists in the file or not. But if we write one or more keys and flash into disk row set, sometimes row ranges are overlapped. So for example, you want to write for Chris into Kudu. In this example, Chris is overlapped in all disk row set because all of them has range from A to Z, so it needs to check all of these three disk row sets. And we have to perform blue filters to look up the row in these files. That's why we need to reorganize these files on compaction. After compaction, Chris only requires to look up disk row set 4 because it has a range from A to I, and so other disk row set 5 or 6 doesn't have a range, so which includes alphabet C. So there are a couple of other techniques in Kudu storage compaction. Main idea of Kudu compaction is always be compacting. So, well, one key point of HBase compaction, so for familiar with HBase administration, is to manage major compaction to avoid unexpected compaction storm, but you don't need to worry about it on Kudu. We also use budgeted compaction algorithms, which allows continuous compaction. Basically, for each tablet, Kudu looks at what is the best way to spend a certain I/O budget. If you have 128 megabyte I/O budget, Kudu tries to use it for compaction in most efficient way. Kudu also has physical and logical decoupling. This means that each replica runs compaction at different times. So I don't have enough time to talk this in details, but so if someone is interested in these techniques, please read the document in details. So let's move on to the read path. We saw traditional LSM storage engine has to merge all the memo store and files together in read path. But Kudu doesn't have to perform any merge on read operation. Kudu knows a single row key only exists in one place, so it doesn't have to do multiple access to disk row sets. And the scanning only happens on the few files on disk because Kudu split columns into each file, so you don't need to access to unnecessary files which columns you don't need to use in your query. Kudu uses a method called MVCC, multi-version concurrency control, to ensure that users always see consistent result in spite of concurrent write operations. For example, let's assume you run a query against the pay column at time 0. And then major delta compaction happens at time 10 before you finish the query. But you don't need to worry about inconsistent read. You can read same data when you started to run the query at the time 0 because previous version data are stored in undo records. With this approach, Kudu users doesn't need to acquire logs and scan and analytics jobs, so we will not block concurrent writers on same data, and then it significantly improves scan performance. So today, I showed some kind of technical details about Apache Kudu in this session. So if you're interested in Kudu, so please access to getkudu.io first, and so read some getting started pages or something. So I just saw some kind of URLs here, but so yeah, just going to getkudu.io is pretty easy. And or if you try to use Kudu, just download virtual machine, or so if you're a developer, just download source code and compile it. So there are many materials and papers in the website. Also, you can use Cloud Manager for free. Cloud Manager is our product, but you can use it for free. It's super easy to deploy a Kudu cluster. Or if you have some kind of cloud platform account like AWS or Microsoft Azure or GCP, I recommend to use Cloud Director, which is also our product, but with this provision instance provision, or installs all softwares and does any other bootstrapping process automatically. And Cloud Director is also it's free, and you can just download it and try to use it. As I mentioned in the beginning of this session, we have a big event named Cloud Award Tokyo in November 7th. My coworker also will talk about Kudu in that event. So, but his topic is a bit different from my session today. So it should be interesting. I believe it should be an interesting session. So now, my session is finished, but please feel free to catch me and ask any questions. And I will be around here today. So now we have two minutes left, or?
Yes.
Okay, so is there any questions you have? Nothing? Okay, sure.
Thanks for your talk. So I have a question about the data ingestion.
Yes.
So it looks like great for the many small data ingestion, but is there any concern we should take care when we want to do the many small set of the small and fast data ingestion?
Okay, yeah. So the question is also, is there any concern on data ingestion for small data? And so at least you're familiar with other Hadoop ecosystem like Kafka or HBase, and so such kind of software doesn't have the data type, and you can ingest all kinds of data, but Kudu has data type, so you need to define the data table first, and you cannot put the data in any kind of data. So such kind of schema design is the only concern. So you need to do.
Thank you.
Sure.
Thank you for an interesting talk. What is the killer application for the Kudu. Do you think?
So you mean so killer use cases for Kudu?
Use case, yes.
Okay. Yeah, so there are many good use cases for Kudu, but we put three use cases which is good to use Kudu. So one is some kind of IoT platform which needs real-time analytics, and one is also operational. So operational dashboard. So you need to have some kind of real-time dashboard, and the last one is migrating from traditional data warehouse, which has some kind of which is too slow or too expensive to use. So IoT platform, so for real-time analytics or real-time dashboard or migrating from data warehouse, is these three use cases are most popular for Kudu users.
Thank you.
Now it's time up.
Yes.
Okay. So thank you for taking time and enjoy today's conference.
Thank you very much, Mr. Shimauchi.